On the back of your notes, we're going to find the interval of convergence for a function, its derivative, and its antiderivative. And this is the function defined by this power series that we're going to be working with. All right, so finding the intervals of convergence for each of the following. Well, based on what was said in the two paragraphs on the front part of these notes, based on what was said there, it might be best to find the interval of convergence for the function first. Okay, and then once we establish what that interval of convergence is, well, then all we have to do to find the interval of convergence for the derivative and the antiderivative is just test the endpoints to see if there's been any adjustments we need to make on the interval of convergence from the function. So I think that's our plan. That's where we're going to start. We're going to start with part B first. It would be helpful for a side objective for us to take this power series and do a little bit of expansion. You certainly don't have to, but I have an alternate objective that I want to kind of focus on too. So I'm going to go ahead and expand a few terms. So if n is 1, we're going to get x, etc. All right, so let's find the interval of convergence. So that requires that we do the ratio test. You don't have to write this. I'm just putting a note to myself what I'm doing here. Ratio test. All right, we have to find the radius of convergence first, and that's going to help us find the interval of convergence. So the limit of the nth term, or the limit of the ratio of two subsequent terms. Okay, a little bit of cleanup. The result would be this. All right, let's pull out the absolute value of x and focus our attention on this limit. All right, we see that this limit right here is going to equal 1. So the result would just be that we're going to get the absolute value of x. So by the ratio test, we end up with not a value, we end up with an expression. So if we want this power series to converge, we have to make sure by the ratio test that we stay within 1 unit of the center, 1 value. So the absolute value of x has to be less than 1. So that tells us that our radius of convergence is 1. That also tells us that our interval of convergence right now is going to be -1 to 1. 1 unit around the center, and the center is 0. Okay, so all we have to do to find the interval of convergence now is test the endpoints. So I'm going to start with x equals -1. Okay, so meaning when we go back to the original function, when x is -1, would that series of constants converge or diverge? Okay, if we have -1 to the n over n. Okay, and what we see here, I'm going to put -1 in parentheses, raise it to the n. Okay, this is an alternating harmonic series. It's an alternating series, so we're going to use the alternating series test. There's 2 parts to it, and that test, the alternating series test, is only for convergence. So if we pass part 1 and 2, then we can say that this series of constants converges. And as a matter of fact, I think we've done previous work with this particular series, and we see that it does converge. So converges by AST. So I'm going to include a bracket over here in just a minute. But I'm going to go ahead and test the right endpoint at x equals 1. Okay, go up to the power series. Everywhere you see x, replace it with 1 to get a series of constants, and let's see by using our past test what we have. If x is 1, we just get 1 to the n, which is just 1, and that's 1 over n. This is a divergent p-series. It's specifically the harmonic series. So this series diverges. We won't include the right endpoint. So diverges by p-series or harmonic. Okay, and so all of this being put together tells us the interval of convergence for this function defined by this power series. So interval of convergence, including the x value of -1, it will work. Oh, parentheses here, but the right endpoint does not. All right, so we've established the interval of convergence for the function. So what was said on the previous side of these notes was that the interval of convergence for the derivative and the antiderivative may just change at the endpoint. So I did this first so that we don't have to do the ratio test again. All I have to do is find an expression for the derivative of this power series and then test that new expression at the endpoints here. So that's what we're going to do. Okay, so we're going to do the derivative first and the antiderivative last. So I'm actually going to go to part C next. Okay, so to avoid the ratio test and everything, let me go ahead and differentiate this power series. So I'm going to have f prime of x equals, okay, now I'm going to find the derivative of this nth term. Okay, and I'm going to leave this blank for a minute. That's the whole reason I expanded here, so that we can use the expansion that we get down here to determine what value should I put here for my index. All right, the derivative here using the power rule. Okay, I could do a little cleanup here. I can cancel these two. That's convenient. Okay, so I'm just left with this expression right here. So actually I think I'm going to clean that up a little bit, still holding on to knowing that I need to fill that in. But I'll fill it in through the cleanup. So x to the n minus 1. Okay, so what should go here? Well, it might be helpful to generate a few of the derivative terms here to kind of see what we need to put here. So come back up here. Let's find the derivative of a few terms. So derivative of x, etc. So I'll be left with x. Derivative here, power rule, bring the 3 in front. Looks like I'm just going to get x squared. Okay, I see what's happening. Plus x cubed, etc. Plus dot 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 plus x raised to the nth term n minus 1 plus dot dot dot. Okay, so coming back here and looking at what belongs here to generate this first term, well, if you used n equals 0, you're going to get x to the -1, which is not this first term. It looks like if x or if n is 1, then I'm going to get x to the 0, which generates 1. If x is then 2, I'm going to get the next term, 3, etc. So our index needs to begin with 1. Okay, so back to the objective of finding the interval of convergence for this derivative. I do need to find the derivative of the nth term. Okay, and this is important too, to know this number. That's why we did this little exercise. Okay, but what all we have to do is come back up here and test both x equals -1 and 1 again. So we're going to test x equals -1, okay, into the derivative expression. So we're right here. All right, so test x equals -1. All right, so let's see. So if x is -1, so I'm going to have -1 raised to the, what, n minus 1? All right, so let's look at this series of constants now that I've removed the variable here. I'm going to try the nth term test for divergence. So what's the limit as n goes to infinity? Well, we can see that the exponent is going to vary between an odd and an even number. So let's think about the effects of what that has on our base. So if, for example, n is 5. If n is 5, then I have an even exponent, so the result would be 1. If n is odd, if n is 6, then our exponent would be odd, so the result would be a -1. So it looks like our terms are going from -1 to 1 alternately. Well, if you apply that limit as n goes to infinity, my answers are either going to be 1 or -1, both of which are not equal to 0, so this is a divergent series by the nth term test. Just a note to self. Okay, by the nth term test. Okay, so that tells us back up here that we can't include the left endpoint of -1. So there won't be a bracket, there'll be a parentheses. Let's test x equals 1. Okay, going to the derivative, where am I at? The derivative expression is here. Everywhere I see x, replace it with 1. So 1 raised to any power is just going to be 1. So the limit of that nth term is 1. So it also diverges by the nth term test. Okay, so putting all this together just tells us the interval of convergence is -1 to 1. No inclusion at the endpoints. So we can differentiate this power series. It's just that it's going to have a slightly different interval of convergence than the function when we differentiate. And the last part, find the interval of convergence on the antiderivative. All right, keeping in mind that when we integrate, we introduce a constant of integration. It's kind of common practice to put that c value before the sigma notation. Okay. All right, I'm going to integrate the nth term of the original function. I'm going to leave this blank for just a minute. I'm going to try and look back way up at the nth term. Here it is, and I'm going to do the reverse power rule. So integrating that, reverse power rule. In the denominator we had an n, so I'm going to have to include the factor n plus 1 here. Okay, so I know I'm going to come back here and fill this out, but first of all, let me do a little bit of expansion. Equals the constant of integration plus, well, without knowing what this is, I can't really generate terms, but I'm not looking at doing that. I'm looking at coming back up here and term by term finding the antiderivatives. So what's the antiderivative for this term, this term, this term, this term, which will help us then figure out what our n value should be, our starting n value should be. Okay. All right, so I know I can't have it on the screen, but you probably have it on your paper. So the antiderivative for the first term of the function x, that antiderivative would be x squared over 2. All right, the next term would be x cubed all over, looks like there was a 2 down in the denominator already. And so I also need to divide by the new exponent. So let's do a few of these to see if we can get a pattern. X to the 4th. I think there was already a 3 in the denominator, but I need to divide by the new exponent. And we'll continue this one more time. This would be x to the 5th over, there was already a 4, but I need to divide by the new exponent. So it's kind of shaping up to what I see here. Plus dot 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 plus, and just writing that nth term down again of n. Okay, so here's the expansion that I got by integrating term by term, and then I'm trying to fill this value in right here. Okay, well, let's look at this term. To get x squared, then I would need the exponent up here to be a 2, and I already am adding by 1, so it looks to me like I need to start with n equals 1 as well. I'm not readjusting to 0, because if I readjusted to 0, I'm going to produce a term, if n is 0, that's not part of the integration of the original function. So it's kind of good to work with the expansion, okay, to kind of make sense of the index here. All right. All of that on the side, but let's get back to our objective. What's the interval of convergence, okay, for the antiderivative? So remember, all we have to do is check the endpoints. So we have two tests. All right, so let's test x equals -1. Okay, let's see, where is it at? Here it is, right here. Here's our expression, right here. Well, actually, this whole thing right here. Now, constant, just one finite number, is not going to change the results, so we can kind of put that on hold, ignore that for a moment. When we test x equals -1, we really don't need to worry ourselves too much with that constant. Okay, because one little number is not going to change, the big picture. All right, so x is -1 here. So we've got -1 raised to the n plus 1. So that's an alternating series I see already. Okay. All right, and so since it's an alternating series, I'm going to apply that test, and the short of it all is that it does converge. It passes both parts. So this is converges by AST. So we're going to put a bracket at the left end point of -1. Okay, let's test x equals 1. Okay, and again, the constant we'll just kind of put on hold in our thoughts here and just work with this expression. If x is 1, that's 1 raised to the n plus 1. I'll go ahead and write it, but I think we all see where that's going. That's just going to be 1 over n times n plus 1. Okay. All right, if we're trying to determine the convergence or divergence of this series of constants, we can't use the AST, the limit of the nth term test doesn't work, it's not geometric. I'm trying to think of what's left here. I could do the ratio test, but that seems like a lot of work. Actually, to save some time here, just let you know that this is the direct comparison test with 1 over n squared, that piece series that converges. Okay. And as a matter of fact, when you directly compare it, and this is convergent, this series right here is smaller than this convergent series. Okay, and so that tells us that this series also converges. So I'm just going to say direct comparison with that, and it actually converges. So in the integration procedure of this power series, we gain both endpoints. Okay, so I'm going to say as a result, all of this interval of convergence. So we can certainly integrate and differentiate power series. We just have to be mindful that if we're asked to find the intervals of convergence of those, that we have to test the endpoints to see if we've lost or gained anything at those endpoints.